area.
Okay. Good afternoon, everyone. I would like to welcome everyone to this year's ICS seminar. I am Pavlos Protopappas. I am the scientific director for the Institute for Applied Computational Science. So the ICS seminars consist of talks that they come from industry and academia. It's a mix of topics that cover data science and computational science. So we have topics that various fields, from astronomy to malware to entertainment, neuroscience, etc. The full schedule is on our website if you want to see. There are 7 talks this semester and more talks in the spring. So one of the topics we cover is also social good, and that brings me to the point to introduce our speaker today. I would like to welcome Milind Dambe. Welcome to Harvard as well. This is your first time at ASIS.
Thank you.
Milind received his PhD in computer science from Carnegie Mellon, and now he's a Gordon McKay professor here at SIS. And his research is in particular in AI and multi-agent systems for social good. He has received quite a lot of awards, and we agree not to mention them since he's a SIS person, and you're going to get to know him better. So today he will be talking about AI for social good, learning and planning end-to-end data to deployment pipeline. Please help me welcome Milind.
Thank you. Thank you. Okay. Thank you all for coming. Thank you for this kind introduction and welcoming me to Harvard and for this invitation to give this seminar. So let's get right down to it. With the current progress in AI and multi-agent systems, it is now crucial to lead these advances towards societal benefits. And I'll focus on 3 areas: public safety and security, conservation, and public health. In all of these areas, viewing these problems as multi-agent systems, the key challenge I'll focus on is how to optimize our limited intervention resources when interacting with other agents in these domains. And in providing solutions, I'll present 2 key ideas that cut across. First, multi-agent systems reasoning, computational game theory, social networks, and others. And second idea of end-to-end reasoning from data to deployment. With respect to public safety and security, we have a large number of targets to protect limited security resources, how to schedule or plan or allocate our resources, taking into account a watchful adversary. We've contributed a new model called Stackelberg Security Games and contributed new algorithms that have been in use by security agencies in the United States and internationally. With respect to conservation, we have large conservation areas to protect limited number of ranger resources. We've here contributed a new model called Green Security Games. Concrete example is work we've been doing in Uganda. Taking into account past poaching data, we are able to predict where poachers may set traps or snares, and for the past several years have been able to remove a large number of snares and even get poachers arrested. The model has been extended towards combating illegal fishing and illegal logging. With respect to public health, we have limited numbers of social worker or public health official resources. Concrete example is work we have done in homeless shelters in Los Angeles. Here, using the social networks of homeless youth, we are able to show that our influence maximization algorithms are far more effective in spreading HIV information compared to traditional approaches. We've extended the model towards combating tuberculosis in India, and I'll talk about that, and other such public health challenges. In all of this work, interdisciplinary partnerships with governmental and non-governmental organizations have been crucial. To that end, we've really patrolled with the Coast Guard on their boats in the Port of New York. We've really patrolled with wildlife conservation agencies in forests, such as in Malaysia. Our students have spent time in homeless shelters. We're working with the homeless shelter officials. All of this immersion is important to understand what kind of data to collect, on the basis of which we can build a predictive model, machine learning models that would be able to predict which cases we face are high risk versus low risk. We then want to intervene on them, but we don't have enough resources to intervene on all high risk cases. Our algorithms, game theoretic algorithms, may then select which cases to actually intervene on. But beyond that, it's very important for us to actually test or deploy these algorithms in the field, not only because we care deeply about the social impact, but because this is a good way for us to truly understand what are the weaknesses of our models and algorithms. So in the rest of this work, in this talk, I'm going to talk about the 3 areas I mentioned. This is going to span over 10 to 12 years of the work that we've done in our group. Public safety and security is the first part. That's going to, because that was the earliest part, I'll cover it very quickly, but it sets the stage, it gives us the models that we then will use in the remaining part of the talk. All of the work I'll describe has been published in AI conferences, AAAI, ICHKA, IAMAS, and others. There you'll find the typical simulation results. Today's talk will exclusively focus on real-world evaluations that we've done. If you're really interested, you can look at these edited books that we've published on each of these areas. If you buy these books, then from the royalties, I can take my students out to a very nice dinner. So you can take that as a hint. But more seriously, the key PhD students and postdocs who've led these efforts, I'll have their pictures on the top right-hand corner so you know who led these efforts. So let's start with public safety and security. Clearly, this is a global challenge. Events of 9/11 were devastating for all of us. I grew up in the city of Mumbai, and there we have faced public safety and security challenges continuously. For example, 11 July 2006, bombs went off on trains in Mumbai. My mother was actually traveling in one of those trains. Luckily, fortunately, she just got off the train before the bombs went off. But these sorts of things had raised the issue of public safety and security in my mind. So when the chief of airport police at the LAX airport approached us to improve security, and I'll often refer to LA because I came from USC, that's where a lot of this work got done. So when Errol approached us trying to improve security at the airport, we were all ears. His challenge was somebody driving a suicide truck into one of the terminals, as had happened in Glasgow in 2007. There's 8 inbound roads into the airport, not enough officers to be at all roads at all points to do checkpoints. 8 terminals, not enough dogs. The question for us was, could we propose game theory as a way of optimizing limited security resources? Could we convince the scientific advisory committees that game theory was the right approach? Could we convince our AI reviewers for AAAI and other AI conferences that game theory was the right approach? And most importantly, could we convince the sergeants on the ground that this was the right approach? But that's what we decided to do. So we proposed this new model called Stackelberg Security Games. I'm going to illustrate it using a simple 2x2 example. So imagine just a very small toy example, 2 terminals, 1 police officer. The police always try to protect Terminal 1. If that happens, an adversary conducting surveillance will attack Terminal 2. The adversary gets a positive reward of 1. The police get a negative reward -1. If, as a result, the police were to switch and always protect Terminal 2, now the adversary will attack Terminal 1. Again, the police get a negative reward. The adversary gets a positive reward. So any deterministic strategy an adversary could defeat. If the police were to use a randomized strategy, mixed strategy, 60% of the time they're at Terminal 1, 40% at Terminal 2, an adversary conducting surveillance will only know the police are there 60%, here 40%. What they'll do tomorrow remains unpredictable. These kinds of games are called Stackelberg games because defenders commit first to a mixed strategy, and then the adversary responds. These are security games that are played on targets where payoffs are based on whether targets are covered or not. And we are optimizing our limited resources. We are not guaranteeing 100% security because in the real world, there is no such thing. We are increasing the cost and uncertainty to an adversary in coming up with a plan of attack. So this is how we built Armor for the LAX airport. We start with the game matrix, and I'll come to how we built that in a minute. That's fed into a mixed integer program that provides a mixed defender strategy. Probability that there's a canine patrol at 8 a.m. at terminals 2, 5, and 6 is 0.17. Probability there's a canine patrol at terminals 3, 5, and 7 is 0.33, and so on. And then we sample from this distribution to generate an actual schedule. For example, at 8 a.m., send team 1 to terminal 2, team 3 to terminal 5, team 5 to terminal 6. At 9 a.m., do something different. And this is an actual schedule that's in the hands of the police officers, and they'll execute that. So let's look at how we wrote the mixed integer program. We are trying to maximize defender expected utility. Rij here refers to the reward to the defender if the defender takes a strategy I and the adversary takes a strategy J. Xi is the probability with which the defender takes a strategy I. For example, X1 is the probability we put a dog on terminal 1 and a dog on terminal 2. X2 is the probability there's a dog on terminal 2 and a dog on terminal 3. So for every single combination of defender resources to targets, we have a probability variable. This is adequate for these airport purposes. It becomes more difficult as we try to scale up, as I'll come to in a minute. Qj is the adversary's response. We model the fact that the adversary is able to observe our mixed strategy or randomized strategy, and then they do their best response, the best plan of attack. And so that's also encoded. Now, where did the payoffs come from? So the threat here was somebody driving a suicide truck into one of the terminals. The loss to the defender would be the loss of human lives that would occur if such an attack were successful. We had from the airport detailed numbers on how many people were present at different times of the day at different terminals. So on the basis of that, we derived these payoffs. Of course, we understand these numbers are not exact, and we have to be able to handle uncertainty, and we've spent enormous amounts of time dealing with that. But given that we have short amount of time, I'm going to skip over some of those details. And we built this armor system, and this was operational at the LAX airport starting in 2007. So this is the first such application that was built of computational game theory for operational security. And the news media in LAX, local TV stations, soon had news about armor being operational at the airport, and all these weapons being captured, reported in the news just in January of 2009. The LAX airport police were very happy with this, and somebody at City Hall noticed, and because we received these commendations from the city of Los Angeles, so that's me and my students. Up to that point, we had been very fortunate to have received a Best Paper award or two, but this was a very different honor. We were very grateful. Errol Southers even went to Congress to talk about this work in a congressional committee hearing.
LAX is safer today than it was 18 months ago. A team of research led by Dr. Malen Tombe worked with our department to develop armor. This software randomizes our vehicle checkpoints along airport access roads and the deployment of our explosives detection canine teams throughout the airport.
Newsweek had a story about armor saying throwing a digital cloak of invisibility, which led my colleagues at the next AMAS conference to ask me if I was working on a cloaking device. But this did get the attention of the federal air marshals. Their challenge was assigning air marshals to flights. So now we have a problem of even the thousands of flights that fly overseas every day. We are assigning air marshals to those flights. If you just imagine 1,000 flights and 20 air marshals, the game is massive. Here along the rows are all possible ways we can assign air marshals to flights. We can assign air marshals to flights 1, 2, 3, 1, 2, 4, 1, 3, 5, so forth. And the adversary could attack any of these flights, flight 1, flight 2, up to flight 1,000. There's 10 to the power 41 different rows in this game matrix because there's 10 to the power 41 different ways in which we could assign air marshals to flights, which means that there's 10 to the power 41 xi variables in our mixed integer program, which means that program cannot run. However, we devised the new exact algorithm and incremental strategy generation approach, the first such algorithm for Stackelberg security games. It starts by taking a master problem that has a small number of pure strategies, and then a slave problem that iteratively adds pure strategies to the game matrix. And we arrive at a global optimal, except that this global optimal can be arrived at with just 1,000 pure strategies with a much smaller game matrix rather than the 10 to the power 41. So this is how we built Iris for assigning air marshals to flights. If you've been on a US air carrier, United, Delta, American, and so on, whether there was an air marshal on your flight or not internationally may have been determined by this program. In 2012, we were very honored. Our work was again mentioned in a congressional committee hearing, and the certificate of appreciation from the federal air marshals. This got us invited by the to the US Coast Guard to improve patrolling in different ports, including right here in Boston. So for them, we built this system called Protect. So Protect is an acronym. This is to tell you that we spend enormous amounts of time trying to come up with good acronyms. We generated patrols in different ports, Boston, Los Angeles, New York, One key challenge was generating patrols around the Staten Island Ferry, which is a moving target, continuous time games. And so these patrols are our algorithms at work that completely changed the way the Coast Guard did these patrols. In the interest of time, I'm going to skip over the details of this continuous time solution and just get to the point that the Coast Guard were satisfied. We got this meritorious team commendation from the commandant of the Coast Guard in a surprise ceremony at the Atlantic Area Headquarters. And again, a mention in the Congressional Committee hearing from the Coast Guard.
We're working with the University of Southern California to utilize game theory as a way of optimizing and scheduling our patrol. Makes it harder for somebody to anticipate where the patrols will be.
So in all of this work, this data to deployment pipeline has been crucial. Field tests have often revealed new research challenges that we couldn't anticipate in the lab. We developed schedules, for example, for the LA Sheriff's Department to check people traveling without tickets on trains. The schedules looked great in the lab when the officers went out in the field trying to look for people traveling without tickets. We realized that they would often get interrupted. There were people who hadn't paid their tickets for many times. Some of them, there would be altercations, maybe there were arrests. And all of this would mean all our optimization was out the window. So we needed a different method where we needed interruptible schedules. And so this was a whole new research problem that we had to solve. And so these kinds of issues only come up because we went all the way to deployment. Today, we are very thrilled to see security games work being picked up in many different parts of the world, many different applications, whether in Singapore to generate patrols, work recently in Israel to use security games to reduce traffic accidents, and so forth. So I'm going to talk next about security game applications in Africa for wildlife conservation, but before I do that, let me briefly mention some of the real-world evaluation that we've done. There's a lot of it, but in the interest of time, I'm just going to touch upon a few. The basic idea is to show that security games are superior in optimizing limited resources compared to traditional approaches of human scheduling or simple random approach. So first, I'm going to show you something right here in Boston. We are here. So this is the Coast Guard patrols in Boston before Protect was deployed. Along the x-axis are different days of the week. Along y-axis, somebody went out to check how frequently were different targets visited. The green line on top, how frequently was a target visited on day 1, on day 2, on day 3. Each line refers to a different target. Two main points to note. There were very few patrols on day 2 of the week. This was a great day to attack the port of Boston. And all those lines crisscrossed, meaning sometimes the target was more important, next day it was not important, third day it was more important. That's not the way targets actually are. So this is after Protect was deployed. There's no dip on day 2. More important targets are visited more, less important targets are visited less. On any given day where the patrol boat will go remained unpredictable, but on the whole, the more important targets are visited more. From before to after, there was 350% improvement in defender expected utility. We also did controlled experiments. For example, we sent patrol officers, 90 of them, on trains in Los Angeles. Once they were scheduled using human schedulers who spent 2 days trying to come up with the schedules, and once using our game theoretic approach. And then we had external observers who did not know who had generated which schedules, sitting at each station evaluating these patrols along 10, 12 questions. The conclusion was that the human schedulers were worse than the game theoretic schedules. So the humans had spent 2 days coming up with a schedule, but in the end, their schedules were worse than the game theoretic approach. We also sent patrollers on trains trying to catch fare evaders. So for 21 days, they patrolled. They didn't know what kind of schedule they were getting, but sometimes their schedules were driven by our game theoretic approach, sometimes using a baseline approach. And the question was, who caught more fare evaders? And what we find is that the game theoretic approach led to 60% increase in the number of fare evaders that were captured. At the checkpoints at LAX, numbers of captures from before to after armor was deployed jumped 5-fold. All of this to show that there's evidence here that the security games approach does improve optimization of limited resources. So let me now move to conservation, green security games. This is work done jointly with Dr. Andy Plumtree, who's a conservation biologist. So this is Murchison Falls National Park in Uganda. Some of you may have visited there. Absolutely wonderful place. These are my pictures of these magnificent wildlife, but they're threats to the wildlife. These traps or snares, thousands of them that are placed in this park to maim and kill these animals. So how to optimize the use of limited ranger resources in protecting these vast national parks? So we introduced this model of green security games. We take a park like the Queen Elizabeth National Park and divide it up into 1 kilometer by 1 kilometer grid square, where each grid square now represents a target. Now we can write our mixed integer program, this is Sackelberg game, to try to solve this. But there is a crucial difference. Now we are not faced these fully strategic adversaries or conducting a big attack, but rather boundedly rational poachers are going to conduct many different attacks. And so they're not going to do this one best response, but rather we have to learn the adversary bounded rational response from the many attacks they've conducted. For each grid cell, we are trying to learn the probability of finding a snare, a trap in that cell, this function GI based on ranger patrols in that cell, and other features of that particular geographical location. And then we can optimize our patrols based on that. So attention now shifts to learning this function GI, probability of finding a snare in a particular grid cell, based on features that we have. So we have 12 years of poaching data from Uganda, and for each attack that was found, we have distances to roads and rivers, animal density, ranger patrol frequency, slope, habitat, and many other features. So the only challenge, though, is that when the rangers report they found a snare, a trap, they have found it. It's a positive instance, yes. When they say we did not find anything in this particular grid square, we can't be sure. Maybe they didn't walk enough in that grid cell. If they just walked a little bit more, they could have found it. So positive instances we are sure of, negative, not so sure of. So this is sort of this positive and unlabeled data set that we have. And so how do you deal with this uncertainty in the negative instances? So we've constructed this ensemble model where we build many different training sets. So for example, in one training set, we remove all negative instances where the rangers have walked less than 1 kilometer in that grid cell, because we don't trust all those negative instances. And we construct a classifier. In another, we remove all training instances where the rangers have walked less than 2 kilometers and construct a classifier for that, because here we say we don't trust any negative instances where rangers have walked less than 2 kilometers. And we build a whole set of classifiers like that, and now we have an ensemble that we can use. So when a test instance comes in where a ranger has walked only 1 kilometer, we say use these 2 classifiers. When rangers have walked more than 2 kilometers, say use these 3 classifiers. And it's in this way that we are able to make predictions about where rangers will find traps. So we, of course, did many simulations in the lab. We are able to show that in the lab, our model performs better than standard machine learning approaches. But this was clearly not adequate for our colleagues in the field. They wanted to see a real-life test being done in the field. So for them, we predicted these 2 9-square kilometer areas that were deliberately chosen in the Queen Elizabeth National Park, where there were infrequent patrols, and also where there's not previous hotspots. So if you look at where we have asked them to patrol, we had asked them to patrol these green dots. These don't overlap with the red dots. Red dots are where previously traps or snares were found. So we're not asking them, go back to where you found stuff, but go to new stuff. And now this was done 1 month before a conference deadline. So if traps were found, we're going to write a paper. If there are no traps, there's no paper. And then rangers went out, and they would go out on patrol. Every day we would get an email from our colleagues in the Wildlife Conservation Society as to what happened. Initially, nothing, nothing, nothing. Then one day, sad news, a poached elephant with its tusks cut off. So the machine learning system was asking us to go in the right place. Unfortunately, we were too late for this elephant. Then great news, a whole elephant snare roll was found and removed. So poachers were active in the area. They were killing elephants, but before they could kill the next set of elephants, we were able to remove this elephant snare roll. Then a whole antelope snare, about 10 of them, removed. And so I had promised my students for every single snare that would be removed, I would buy them a drink. At this point, it's like no more. Our paper outlines our base hit rate versus historical hit rates and so on and so forth. So this started to give us confidence that these machine learning techniques are working in pointing us to the right direction to find these traps. But one criticism is that this is Uganda. You go to a national park where people haven't patrolled before, you're going to find some traps or snares lying around. To combat this criticism, we devised a larger scale experiment in 2 national parks in Uganda for 6 months. So here we outlined 24 separate areas. Some our model had predicted as high risk, some our model had predicted at low risk. This was not made available to the rangers, and we asked them to go and patrol for 6 months, and then report back what was found in each of these areas. And what we find is where we predicted high risk, indeed more snares were found. Where we predicted low risk, lower number of snares were found. And when Murchison Falls, we divided high, medium, and low, and our predictions turned out to be right. So now we're building up even more confidence that these models are going in the right direction. But it is my belief that we have to stress test these models continuously. So most recent work has been going on in Cambodia in the Sri Pak Wildlife Sanctuary, place where tigers will be reintroduced after being decimated from Southeast Asia. So we were just in Sri Pak this spring. So this is my pictures. This is with one of the rangers. This gentleman was a Khmer Rouge soldier previously, has become a ranger. Other pictures, poachers being captured. And so again, we sent them our predictions of high risk, medium risk, low risk areas. And these are pictures of snares being captured, really heartwarming pictures that these predictions are working. Again, our predictions work out. And the numbers of snare captures jumped 5-fold from before. So this is really saying that these techniques are helping us save wildlife. And so one of my best emails I received this spring was from Rohit Singh, head of WWF, saying, Milind, I'm super excited with these results. Let's get going with other countries too this year. And so that's what we are doing. We're trying to go around the globe. So in collaboration with SMART, which is this collaboration of WWF, WCS, and others, and AI for Earth, which is this Microsoft program, which is helping us, we're trying to take paws around the globe. So this is our trying to take this software to protect protect wildlife in 600 national parks around the globe. And so hopefully this will also be extended to protecting forests and fisheries. Now, as we try to do that, many interesting research challenges are bound to come up. So one that is going to happen, because not all national parks have the right kinds of data, is that in some parks, we will have not enough data, which means we may not learn accurate enough adversary models, which means there may be errors in how we recommend patrols. So one approach to try to address this is this idea of game-focused learning. So to understand that, let me take a step back and talk about how this data to deployment pipeline works. This pipeline works stage by stage. So essentially, you have a prediction engine, a machine learning system that says, I want to learn the most accurate model possible. And then we feed it to an optimization engine that will use mixed integer programs or game solvers or something to come up with an optimized solution that tries to maximize decision quality. Now, we're really interested in this. We're really not interested in just getting a maximum accuracy. And in fact, maximizing accuracy in our machine learning programs may not lead to maximizing our decision quality. And so we don't necessarily want to do this stage by stage, but instead automatically shape our model loss by feeding the optimization problem inside the training loop of our machine learning. Let me illustrate this in the example of this wildlife conservation. Supposing there's 4 targets, 4 areas where wildlife is being hunted. And we want to learn this GI function, the probability of we're going to try to find the snare. So a machine learning program will try to find, try to maximize accuracy of adversary target value estimates for each of these 4 targets. It's trying to get the GI as accurate as possible for each of these 4 targets. Following that, we're going to optimize by generating patrol coverage for each of these areas. However, supposing the 2 targets that are shown have the largest effect on our defender expected utility. That means we really don't care about getting estimates right for the other 2 targets. So we can do that so that instead of maximizing accuracy, basically we're trying to maximize defender expected utility inside of our machine learning loop. And this, in simulation, we can show this is right now in simulation, leads to much higher performance. So basically, the blue line is when we modify our machine learning loss function based on what we are actually trying to do, the optimization problem we are actually trying to solve. And the orange line is the stage by stage, where machine learning is just trying to maximize accuracy, and then separately, we do this optimization. When there is low amounts of data, the two are very different. Our blue line is higher. As you get more and more and more data, and the model becomes more and more accurate, at some point, the two begin to catch up. But since we are going to face large numbers of parks who may be along the blue line, so we believe this approach would be helpful. Let me now turn to another area of future work that we are pushing, and that is using real-time information with drones. So far I've talked to you about learning predictions from historical ground truth. We have been working with Air Shepherd, which is an NGO that flies drones in South Africa, and they collect infrared video over parks. And then there's a van where a human being sits looking at these videos, trying to find poachers in these videos. And you can imagine 2 a.m. in the night, a person is looking at these images, trying to find poachers and animals. It is not easy. So for them, we've built a system called Spot, which automatically detects humans and animals from these videos. And the idea is that now we can alert our rangers and say, hey, there's a poacher in your park, go arrest them. So this is how it is supposed to work. Air Shepherd will fly the drones, the video is beamed back to the van, Spot is running, automatically detects poachers, and then they're supposed to call rangers and say, hey, poachers are in your park, go find them. Except that there's not enough rangers around. The probability that there may be a ranger there may be only 0.3. What do we do for the rest of the time? So one thing that our colleagues in Air Shepherd have done is deceptive signaling to indicate a ranger is around. So when there is no ranger, it's flying at night, so it'll turn on its lights and fly towards the poachers to scare them, to say, hey, rangers are coming. And they see poachers sometimes running away like that. But poachers are smart. So if you always do this, they'll figure out that there is just no rangers are actually showing up. So we want to be deceptive in our signaling. We must be strategic in our deception. And this strategic deceptive signaling has been the PhD work of my student, Haifeng Xu, who's a professor in University of Virginia now. So here's how it's supposed to work. Supposing we have a 0.3 chance the ranger is present. Then when a drone flies overhead, the drone knows probability of 0.3 ranger is present. Poacher knows probability of 0.3 ranger is present. But the drone also knows something the poacher doesn't know, whether there's actually a ranger here or not. So when there is a ranger truly present, they are going to honestly signal to the poacher that, yes, there is a ranger by turning on their light. Now we have truthfully signaled that in these cases there is a ranger. When there's a 0.7 chance of no ranger, again, the drone knows there is no ranger. The poacher doesn't know that. With a 0.3 chance, we are going to signal to the poacher that there is a ranger. From the poacher's perspective, there is a 0.6 chance of seeing the signal, except that half of the times there is a ranger, half of the time there is no ranger. The poacher doesn't know which one. But the probabilities are adjusted in such a way that it is in the best interest of the poacher to believe this deception and run away. And then we'll be honest and say signal when there is no ranger. So the deception is strategically manipulated so that it's in the best interest of the deceived party to believe the deception and run away. And it turns out that this signaling actually reduces the complexity of doing equilibrium computation. So this work is going on full swing. There's going to be a big workshop here at the Harvard Faculty Club that we've organized, bringing together SMART, our researchers who are working on PAWS, the software program, Spot, and others, and Microsoft AI for Earth, to try to see how we can now lay the path forward for continuing this move forward. Okay, so the last part of this presentation is going to be about public health. This is work done mostly with Professor Eric Rice in the School of Social Work at USC. And so here, the first domain that we're looking at is this challenge of HIV prevention amongst homeless youth. There's 6,000 homeless youth who sleep on the streets of Los Angeles every night. HIV is a major challenge because rates of HIV among the homeless youth are 10 times the rate of normal house population, often because of exchange sex and others. So homeless shelters run campaigns to try to spread information about HIV. They do so by recruiting key peer leaders to spread HIV information. Now, the idea is that they'll recruit these youth who are peer leaders, educate them about HIV, and through the social network of these youth, the information is supposed to spread in their population. Now, these are real social networks. These are not Facebook. They don't have Facebook here. This is face-to-face communication. This is the traditional problem of influence maximization in computer science. You have given a social network. You're trying to pick K peer leader nodes with the idea of spreading information, maximizing expected number of informed nodes. Information is assumed to spread here using this independent cascade model. So if you inform youth A about HIV testing, there's a probability of 0.4 here that's shown that node B, who's adjacent to node A, friend of node A, will be informed about HIV testing. B will inform C, and so on. Information will spread. Immersion in this domain, though, showed us that there's no chance of really understanding this probability. So when we inform youth C about HIV testing, the chance that youth D will be informed, we can't be sure what's the probability. So we can model this as there being some probability distribution over what's the probability with which information will spread. And we can say that we have even uncertainty over the mean of this distribution. So now the challenge is, how do you spread information? How do you pick peer leader nodes when there's uncertainty in how messages, what's the probability with which messages will be transmitted? So we've come up with this algorithm, which essentially modeled as a game against nature. So the algorithm is trying to come up with a policy to pick peer leaders, and nature is trying to choose parameter settings to get our algorithms to perform as worse as possible. And so the payoff in this game is the ratio of the performance of our algorithm to the optimal in this setting. So we are going to choose a policy, pick these 3 peer leaders, let's say policy 1. And nature is going to set parameter values to cause our algorithm to perform as worse as possible. We may choose policy 2. Again, nature may choose different parameter settings. So this is a kind of game that we can construct, except again, this game is very large because we have millions of ways we can choose youth in a big network. And nature has many, many different parameter settings. But we've seen in the past how we can solve large games by using iterative procedures. So we use that to solve these big games. And we can arrive at equilibrium even though we don't have to enumerate all these large numbers of strategies and show that we can converge with approximation guarantees. There's a second challenge we have to deal with. Supposing we want to bring in 12 youth in order to educate them about HIV testing. The homeless shelter, though, can only accommodate 4 at a time. So we're going to bring in the first 4. We say, OK, these are the 4 youth who should show up for our first training session. But on the day of the training, what we find is 1 youth on their way got arrested. A substitute was sent. Another ran away because of the unfortunate circumstances in which they are. And so therefore, instead of the 4 we really wanted, some different 4 showed up. Which means the next time we select 4, we have to be mindful of who were the first 4 who showed up, because we still want to maximize expected influence. So this is the idea of planning under uncertainty. And this can be done using POMDPs. This is a classical model, of course, in AI. And to solve these large-scale POMDPs, my student Amulya Yadav came up with this idea of POMDP partitioning based on sub-communities of homeless youth, youth who plays basketball together, youth who hang out on Venice Beach together. And so using this POMDP partitioning, we can solve these policies very quickly. So with all of this in place, we built a system called Healer, and now it was time to go out in the field and test it. So we recruited 170 homeless youth, one cohort under the Healer condition, 1 for Healer++. So these are our 2 algorithms, and then 1 with degree centrality, which is selecting the most popular youth. This is the traditional approach with which the homeless shelters have worked in terms of spreading HIV information. We selected 12 peer leaders in each case, identical numbers. And then we had our social work colleagues educate these youth about HIV testing. The question is, which approach will lead to maximum number of information spread among these three approaches. So our algorithms are basically the traditional approach of choosing the most popular youth. And the result was that our algorithms led to 75% of those youth who were not informed, those youth who we had not brought in as peer leaders to be informed about HIV. And with the traditional approach, only 25% of the youth, non-peer leader youth, got informed about HIV. So clearly, these AI algorithms were being far more effective in spreading HIV information. Okay, so they got the information. Were they actually testing for HIV? So we looked at that, and we see 30 to 40% under our algorithm started testing for HIV, but not with degree centrality. So this is showing us promise in terms of having this program be useful in other cities. But there is a challenge here, which is that we started out with the assumption that we have a social network of these homeless youth. But in reality, we don't have that social network in hand. So what can we do? So the idea is that can we run a simple survey at the, in the homeless shelter of just a small fraction of the youth and collect a sample network. So if we can sample about 18% of the youth and then use that to generate our peer leaders, would that work? So we built such an algorithm. In simulation, it ran great. But the question was, how does it work in practice? Again, we recruited 60 homeless youth, 12 peer leaders, ran a similar experiment. So now we have only working with a small sample of the network rather than the whole network. It works out that this sample was just as effective as having the whole network in hand in terms of spreading information and in terms of HIV youth who started testing for HIV. So this shows that the sampling algorithms are useful in collecting the right kind of information that we need in order to spread HIV information. So now we can start to think about rolling out these kinds of programs potentially in other places. So our collaborators were thrilled with these results.
Beautiful way to kind of like marry this tech world with this social service world, like, and how we can kind of go deeper and impact young people and elevate them.
If this group became a really big thing, it could really help out a lot of youth.
And so we've currently completed a study with 900 homeless youth in 3 different homeless shelters, and hopefully we'll be able to look at these results very soon. The last part of my presentation is tuberculosis prevention in India. Tuberculosis is a major disease. Maximum number of people killed on this planet of any infectious disease is due to TB. In India, it's a major problem. 500,000 deaths a year, 3 million infected per year. And we are focused here on patients in low-resource communities and the challenge of non-adherence to TB medicine. So once a patient is infected with TB, they have to really take their medicine for 6 months. And often people will drop off of treatment. So now there's these digital adherence technologies. So basically patients have on their pill packs a number. This is a random number. So when they open that pill, there's a number. They're supposed to call it to say, hey, I opened that pill pack and I got this number. And government officials can then track who's taking their medicine, who's not, and then call the person if they haven't taken their medicine for 3-4 days, or go to their home and say, hey, you got to take your medicine because not only bad for you, bad for everybody if we have drug-resistant bacteria. Of course, if you wait for 4 days for somebody not taking their medicine and then go to their home, that's too late. Could we predict in advance who's at risk of not taking their medicine so that people can be, health workers can prioritize those patients before they stop taking their medicine? So that's the challenge that we have been working with. So we have data from the state of Maharashtra in India, 15,000 patients, 1.5 million calls. This is work done jointly with an NGO called Everwell. Based on that, we are trying to predict high-risk patients. So it goes something like this. Patient 1 here didn't call on day 1, called on all 4 days. Patient 2 called on day 1, day 2, did not call on day 3, called on day 4, did not call on day 5. We have the time of the call as well as when they called or did not call. And based on this, if we can predict in advance that these 2 patients are the high-risk patients, pay attention to them, these are the ones who next week may not take their medicine at all, then health workers can pay attention to these high-risk patients, because each health worker has a caseload of 100, 150 patients. They can't possibly call all of them. Here we have told them these are the 2 people you have to pay attention to. And then we can prescribe to them, okay, you go to the homes of these patients and go talk to them so that they can start taking their medicine. So We ran this prediction algorithms using LSTMs or random forest, and here are results compared to the baseline that has been implemented. We are able to boost the true positive rate by 35%, reduce false positive, and if we include our decision-focused learning, integrating the decision-making within the prediction loop, then we get further improvements. So this is the only result that I have that is purely in simulation. We haven't yet tested in the field. We are very eager to do so in the fall. And so the co-founder for Everwell, Bill Thies, has talked to us saying this work has a potential to save a lot of lives. So we are really eager to try and move forward on this. There's many other challenges we've looked at, whether it's suicide prevention. This is ongoing work with my student, Ida Ramtalabi, that's going on. Childhood obesity prevention, and so on and so on. But given the time, I'll just start summarizing, start wrapping up. So the focus of our work is really trying to direct AI and multi-agent systems for social good. We've looked at public safety and security, conservation, and public health. And there is a shared multi-agent challenge of to optimize our limited resources. And a solution approach that cuts across, that's based on computational game theory, social networks, and other multi-agent reasoning techniques. And often, as we deploy things in the domain, we realize lots of new research challenges. And that leads to newer models being recommended by us, newer algorithms being developed. As we look to the future, I see AI as having tremendous potential in improving society and fighting social injustice. And to that end, it's vital to bring AI to those who have not benefited from it in the global south, and to embrace interdisciplinary work, whether it's with social workers or with conservation scientists and others. As we think about AI for social good, a key challenge, though, is to make sure that we are not stuck in the lab, but we are out in the field, because that is the way in which we can truly test things out in the field and also achieve societal impact. I'll end by thanking all the different collaborators from all these different government and non-governmental agencies, because they are the ones, whether they're conservation, these are rangers who are out in the field putting their lives at risk trying to save wildlife, or social workers, whether they are in Los Angeles or Mumbai trying to save HIV patients or TB patients. These are the workers who really inspire us in this work. So thank you for listening to me, and I'll be happy to take any questions.
You talked about your work in preventing attacks to airports using game theory. Would the same approach be useful to an attacker to estimate the best day to attack the airport as well? So could this be
So no, that's an excellent question. So we've assumed a Stackelberg model where basically what we've said is our strategy is completely known. And so, it's like we assume the adversary already knows everything. And so in that way, there's no gain an adversary would get from getting our code, getting our model. I mean, they know, we just assume they already know everything. And so there's nothing extra that an adversary would get from getting access to whatever we have. The only thing they shouldn't have is the random seed that is used that day.
Well, you're trying to maximize results from limited resources, but can you also at the same time begin to predict how increments in resources could actually produce more beneficial results, given that there's a kind of diminishing marginal return here? But can you make recommendations to budgetary authorities or legislative bodies on, if you just do this much more resources, we can get this much more out of it? You reach that stage?
So we have done some of that work. We have we've created these sorts of charts and shown how much impact improvement or reduction in resources can be, so a lot of this work we have done, some of this we have published and so on. Just an interesting side note, so we tried to do this at the LAX airport just separately, and then there was a strike by the LAX airport police, or there was some negotiation that was going on between the airport police and the management. And then one day I was driving, and on CNN there was news about this dispute, and the airport management saying, But now with AI, we can manage with limited resources, and that really scared me in terms of we don't want to be in the middle of this negotiation. And so it's really important to take whatever results we have in proper context. So we've provided these results where we can try to provide the right kind of context so that people can make the right kinds of decisions without. So in short, we've done this work, but there are implications that we need to be mindful of, that people don't take these results out of context.
Are you working with Esther Duflo at the Poverty Action Lab down at MIT to integrate her approach with your
I would love to.
strategy?
I would love to. We haven't connected. I've heard about that work, but we haven't connected. Would love to. Yes, absolutely.
In the example about HIV, you mentioned that the algorithm was better than the degree centrality method. So what's the real life intuition around that? Because we all assume that being the most popular will give you the most influence, right?
Right. So the thing that happens is that this is a network which has, say, kids playing basketball. They hang out together, kids hanging on Venice Beach together. They have a separate sub-community. And then, so you sort of have all these different sub-communities, and then some popular kids are in the center of the network. So when we choose just the popular youth, basically you hit the core of the network, the central part of the network. There are many of these youth. They're popular. They all know all the popular kids. So you just hit the core of the network again and again. And you don't reach the strategic peripheries. You don't get people. So what our algorithm is doing is picking these strategically placed youth in these different sub-communities rather than just picking the center of the network.
So there's an overlap problem.
That's right, exactly. And my friend Eric Rice, who I did this work with, compares this to hiring your high school football team to spread information, as opposed to hiring the Breakfast Club to spread information, and saying that that's what our algorithm tries to do.
So I had a question about the tuberculosis systematic adherence problem, where you try to predict who doesn't take their medicine based on the prior phone calls confirming that they did indeed take their medication. So I'm curious to know, what about people who did take their medicine but just don't call? I could imagine that being a large portion of patients.
Yes. Right. No, so I think so that's a very important question. So some of the ways in which so in the data we've accounted for this, and the paper has all kinds of details. But in reality, what happens is that, the health workers will call a patient saying, hey, you haven't been calling, what's going on? And they'll say, well, I've run out of battery, or I couldn't, I run out of coverage, or whatever it is. And then they'll manually enter those entries. And so sometimes you'll see manual entries from health workers if they know the patient very well and that they've been taking their medicine and so on. But these are some of the major challenges that we face in dealing with this data, is that there's problems like what you've pointed out. There are other kinds of things where if you just take the raw data, you'll see, okay, the patient didn't take there's some patient didn't take a medicine on day 1, day 2, for a whole week, didn't take their medicine. And then next day, they're just absolutely taking their medicine every day. And so if you use a machine learning model just as is on the data, it may say if there's a patient who doesn't take their medicine for many days, they immediately will start taking their medicine from day 7 onwards. So it's like, what's going on? Well, that's the day when the health worker went to their home and really shook them and said, you have to do this. And then they started taking their medicine. So this kind of data has to be filtered out in trying to come up with, trying to learn a model, because we don't want exactly the wrong inference, because the data doesn't record when the health worker went to people's homes and intervened and what behavior change that caused. So there are many fascinating challenges like these, and we're not the first to have noticed these kinds of challenges with, trying to do data mining type work. But there are many challenges as we try to move forward in this domain.
In the problem formulation where you phrase it as a game between yourself choosing a strategy and nature choosing the worst possible parameters, what was the reasoning for why nature always has to choose the worst parameters? Why couldn't nature choose the median possible parameters, and that could change what the optimal strategy is.
So this is being robust to the worst case, so we are being pessimistic. And this is, there are many approaches in optimization, robust optimization, where you try not to be as pessimistic. But it worked well in practice, as you saw. But there are indeed improvements possible where instead of being so robust, being so pessimistic about how nature would behave, you could potentially do better by assuming, like what you're hinting at, somewhat of a less pessimistic approach. So a lot of these things are very exciting because there are many interesting computational challenges. And so what we find very interesting is the fact that we're trying to solve these problems, but hidden underneath are these many interesting AI problems that need a lot of work as well.
With the PAUSE project, now that you want to roll it out to many national parks, you had mentioned that there are some national parks that don't collect as much data as other ones. Is the strategy to start with a kind of more of a population model, or try to compare that national park and try to find a related neighbor and start with that type of model, then continually learn as more data comes in for that specific national park?
That's a really, really great idea. We hadn't thought, we had thought of that. So that's a really great idea how to proceed. So one of the things we were thinking about was at least alerting the park. So that's kind of active research right now, alerting the park that, look, we really are not very confident about the predictions we're making. Could you send out your rangers for 10 days in this area of the park because we want to collect data? And that would really give us a big boost in the confidence we have in these predictions. But what you're suggesting is that if in the same country or similar geographical area, there's another park, maybe you could use that data to make predictions. So that's a very interesting direction that we have not pursued, but could be very interesting to pursue. That's transfer learning, and so that's something we would be very interested in trying to pursue. Yeah, that's very good. Thank you.
I would like to say this work feels impressive to me. I'm a student at the Kennedy School down the road, and I'd like to ask, what are the challenges, in your opinion, in scaling this approach? Are you limited by the number of students that work with you, by your own time, by the number of public servants you can speak with? What are the boundaries? Thank you.
So I guess one of the limitations is that this is all work with homeless populations, or wildlife conservation agencies. So at some point, somebody has to pay for sustaining the solution beyond the prototype. So PAUSE, for example, we are fortunate and Microsoft jumped in and they supplied some engineers and so on, and SMART has money to support scaling up. But we certainly can't do it on the backs of our students. And so there's always this point where the work becomes good enough. It seems like everybody's happy, and now we want to scale up, like with the homeless shelters. Yes. And then who's going to come in and say, we'll now pay the paycheck to get it to scale up? That's been one of the frictions that we've had. In the public safety and security arena, because these are public safety, like Coast Guard and so forth, they have some funding, so that's one way to try to deal with that. But like this tuberculosis prevention or suicide prevention or some of these challenges of childhood obesity prevention, we need a mechanism to allow us to go from these prototypes. And so that's always the struggle, to find someone who can help us do that. And so one of the things that we've been trying to do is to try and talk to Microsoft, Google, others, to see if they may be able to jump in, help us out in terms of scaling, and we can collaborate with them. So that's one of the things that we are active. But if you have a solution for that problem, I think that's the part where we are limited.
This is actually the purpose of my MPP, so.
Awesome. Maybe we can talk more after.
Okay.
Sure.
Long term, going back to the poachers and the outliers that you don't pay attention to, this is related, I think. Long term, as the poachers learn, do you have the capacity to adapt, or do you need a structure that will permit you to adapt as the poachers learn?
So as far as the immediate learning the poachers may have, we are continually observing the data and continually updating our models. So I think we may be able to deal with that part if there's a small scale adoption. So one of our colleagues is pointing out, so idea being they're not reading our papers and so on. But what if they figure this out and start to deceive the program in some way? And that may be what you're pointing out. So they intentionally try to deceive the machine learning program, and so then that will become an interesting problem to deal with. So we're not there yet. That's what we have repeatedly heard. But that's kind of an interesting direction to think about. If people figure out that these programs are really effective in targeting and removing snares and so on. And in Cambodia, when our prediction started working, there's been more confrontation with the poachers. The rangers have been shot at. And so just before we went to Cambodia, in fact, one of the rangers was sent to the hospital because they got shot trying to recover these snares and so on. So clearly there's some recognition that these models are becoming effective. And so what will be the next step beyond that? So that's what we are, and that's a good question.
I think, thanks, Neil. It was a wonderful talk.
Thank you. Thank you.